Okay, well, as we continue our tour through the human senses, we're going to wrap things up now with the sense of touch, but broadly construed, we're going to call this haptics, and we'll see everything that's entailed in that as we get through these notes here. So let's get going. So we're going to start with basic touch, and that means we're going to talk about tactile sensations, aka the skin senses, right? So we have we're not going to get greatly into the detail of the nature of the receptors themselves, but we have what are called mechanoreceptors embedded in the skin. Mechanoreceptors are specialized neurons that respond to mechanical forces, including pressure, direct pressure, but also sometimes kind of a lateral shearing force across the skin. So if you run your hand across a surface like this, you get that lateral shear across the surface of the skin, and also stretching and pulling of the skin. And so sometimes, of course, we get that in a couple different ways. So anytime you have direct pressure on the skin, you're going to obviously activate some of those direct pressure receptors, but it also pulls the skin a little bit once you push hard enough. And that skin stretch can also be detected. Skin stretch also occurs, though, when you move your body. So if you make a fist, the skin on the back of your hand will stretch, right? And so there's a little bit of stretch recognition that occurs here. Now, historically, research on touch perception has been focused on what we call passive touch research. And the nature of this passive touch research is partly useful for helping us understand the nature of the receptors themselves. So it helps us understand the kinds of patterns and the kind of stimulus that these particular receptors can detect. What's been discovered from this is that there are many different kinds of receptors that respond to different kinds of properties. Like I said, between the shearing force versus direct pressure versus stretch, well, we can map that out by applying those different kinds of stimuli to the skin with an observer who is essentially a participant in this case, who has just got their, maybe, we blindfold them so they can't see the stimulus, and we're going to place the stimulus that they have their hand flat on a table, if you can kind of see in the picture here. And then we apply a stimulus here. I'll use a pen here as an example, right? So you'll apply a stimulus directly to the surface of the skin, like by poking them, for example, right? And we can map out this across different locations of the body even, and that helps us understand some things about differences in tactile abilities across the body. As you might expect, just from your own personal experience and common sense, that your fingertips and your palm of your hand have a great deal of tactile pattern abilities here, right? So that means we can detect very small, fine detailed patterns by touch with our hands, right? And obviously, since we use our hands to hold objects, manipulate objects, explore objects, and touch them, that the ability to extract that kind of information with that particular body part is served by the fact that we have a lot of extra touch receptors embedded into the skin on the surface of our hands, especially fingertips. It's also true, by the way, of the lips, tongue, and lots of the skin of the inside of the mouth, because the ability to manipulate objects when we're eating and chewing, for example, that we can kind of move items around in the mouth and recognize where they are, their size, their shape, and all that sort of stuff. We can do a lot of stuff like that with our mouth as well. So we can map this out. And of course, conversely, on other parts of your body, like on your chest or stomach or back or leg or something like that, obviously we do have touch receptors there, but our ability to detect detailed patterns is certainly questionable. And this is relevant, as we're going to see, because one thing that we might try to do in trying to design ways to communicate information to people through what we're going to call a display ultimately depends on the nature of the sensory system we want to use. When we think of a display, mostly we think about visual displays, right? We have a screen that displays information and we read it, or we think about dials or gauges, I mean to say, that display information on a visual scale like that. But of course, auditory displays, I mentioned warning sirens in the last set of notes on hearing perception, and those are considered auditory displays, but there are also tactile displays as well. And so a couple of examples of this. Sometimes we don't think of it as a display that was necessarily designed to be a display, but in a way, it is a way of providing information. So think about driving in your car. And as you're driving, if there's a change in the texture of the roadway, and you can feel it, right? So in fact, there are on a lot of highways, you're driving in the middle of your lane and you have a nice smooth road surface. But if you accidentally drift off the side of the road, then there are these rumble strip type things on the side of the road that not only make a sound, but also create a vibrating texture or feel that you can feel through. It causes a vibration that transmits through the car and then into your body as you're sitting in the car, right? And you're in physical contact with the car, you can feel those vibrations. And there's lots of different kinds of vibrations that gets transmitted to the driver like that. So not just changes in roadway surface, but changes in engine function, for example, right? If you have a rough idle, you can kind of feel that as a change in the vibration of the car. So there's lots of different ways that we can try to transmit information to a person through a tactile display. Of course, when it comes to reading, we can also look at tactile graphics and Braille as ways in which we can present information tactually to a person. But that means we also need to think about the differences, like where on the body. So of course, people read Braille with their fingertips. But there have been attempts in the past to try to transmit information through other different parts of the body. One example of this, another example is what's called a haptic vest, right? So these are popular sometimes just in video games, so that, you know, a lot of times video game controllers, the game pads that for an Xbox or whatever, will vibrate as a form of haptic feedback, like especially if you're playing a game that involves shooting and explosions. And so if you get shot or there's an explosion, you'll feel that vibration through the controller. But you can also have wear a vest that will also vibrate and create the same kind of tactile sensations that perhaps increase the overall realism of the game, but also just provide information to you as the player of the game. But in addition to that, some researchers also came up with an invention this was decades ago, called the Opticon. And what it was designed to do was to be able to read information visually by a light pen and convert that into electrical impulses that can then be displayed as a tactile pattern on any number of body parts. And one of them was a vest that was designed to strap to a person's back and then display letters on through a tactile stimulation array on a person's back. Now, if you've ever played this game when you were a kid, maybe where you try to draw a letter and write a message by running your finger across someone's back, you would know how difficult that is to accurately kind of guess what somebody's trying to spell out on your back. And so actually using a device that would do this exact same thing through these actuators, tactile actuators on a vest strapped to your back, you can see that this doesn't work very well, right? So this just helps us understand that when we look at this passive touch research, understanding the distribution of receptors across the body and their function and the way in which they can detect tactile patterns is an important thing to do. Now, in fact, I'm going to jump ahead a minute because I want to talk some about how do we measure these tactile patterns and display different kinds of patterns so that we can actually see how much pattern recognition and detail recognition can occur on different body parts. And so we have this measurement. We're interested in what are called spatial discrimination measurements. And what that simply just means is discriminating the location of points of activation on the skin surface, right? So the first one is called the 2-point Lyman test. And that just means I'm going to simultaneously apply either 1 or 2 points of contact to a person's skin. So I've got 2 pens here now. I'll try to do this, get them in front of the camera here, where I come down on my skin at the same time with both points at the same time. And a person, if I did this to a research participant, I would, excuse me, again, have them be blindfolded. And I would ask them, how many points can you feel? Does it feel like one or does it feel like two, right? And so I would be able to either, sometimes I would place these 2 points very, very close to each other, like 1 or 2 millimeters apart, right? So they're very super close to each other. And if you do this test, like say on a person's arm somewhere, like up on the side of their arm or on their back or leg, like I said before, it's very likely that those 2 points of contact that are so close to each other are actually only going to stimulate a single neuron, right? So there's so few neurons spaced so far apart on those different body parts that what we're going to see is that a person, even though you come down with 2 points of contact, a person might say, I only really just feel one, right? So they're not really going to be able to discriminate that until you move those points, maybe again, farther apart. So in this case now, we hold them, let's say a centimeter to a centimeter and a half apart. Then they might be able to say, okay, now I can tell that there's 2 distinct points of contact there. So that's the goal of this research, is to figure out how far apart do the points have to be before a person can actually discriminate that it's 2 versus 1. When you do this on the fingertip or the lips, what we see is that people can discriminate 2 distinct points, even down to that 1 to 2 millimeter distance. But on other body locations like the shoulder and the arm and so forth, then it's going to take like maybe a centimeter or more before someone can reliably discriminate those 2 points of contact. The other method is called the error of localization technique. And what you're going to do here is, again, we're going to come down with a point, but it's a successive application of contact here. So what we're going to do here is we're going to come down in one position on the skin, and then I'm going to lift up, and then I'm going to move my point of contact over, let's say, a millimeter. And I'm going to come back again. And so now I have poked this person twice in 2 different locations. And that's what I'm going to ask our subject here is my second poke is that in the same location as the first, or did it move? And again, just like you would expect to find with the 2-point Lyman test, that when you do this on someone's fingers, they're very good at detecting a small change in the location. If you do it on a shoulder or arm, then you have to move it quite a bit more in order for them to detect the change of location. Here, by the way, is another kind of stimulus that we can use to test these things. And so this is this block of plastic had grooves cut into it, kind of like a comb in a way. And you can see that the width of these grooves and ridges varies, right? So on the top side, it says 1.25 millimeters. So that's how wide the grooves are there. On one side, 4.5 millimeters or 3 millimeters. On the other side there, by the person's thumb. And so what you do is you press this object into a person's skin at some location on the body part, and simply just ask if they can even feel those grooves. And what might happen is that, again, on the fingertip, they will feel even the smallest 1.25 millimeter grooves. But if you apply that side to a person's back, they're going to say, I don't feel any grooves. It just feels like a smooth surface, right? They're too small to be felt. But if you switch it over to the 4.5 or even larger grooves, then they might be able to detect the ridges there, right? So what we're seeing then is that based on this information, we can map out the tactile pattern recognition abilities across the skin, and that relates to how many neurons, these specialized touch receptor neurons, are going to be found within some square centimeter on the skin, right? So the neurons are much more densely packed in some parts of the body. And this actually then corresponds to how much brain area is allocated to different body parts as well. So in blue, what we're looking at here is a strip of cortex from the parietal lobe of the brain called the somatosensory strip, right? And this is the area of the brain that processes all of the touch information. And what we're seeing here and what we've discovered from studying this part of the brain is that different regions of that somatosensory area are dedicated to specific body parts. But importantly, what we see is that the amount of cortex that's dedicated to those body parts depends very much on the sensitivity and tactile pattern recognition abilities of those body parts, right? Not their size necessarily. So you can imagine, larger body parts like the back, your back is a fairly large area of skin. So you think you would have a lot of touch reception cortex dedicated to that. But the answer is no, not really, not very much at all. Conversely, you see the fingers and the thumb or the face and the lips get almost an entire gyrus or even a really, really a-hole gyrus of cortex dedicated to them. So in that case, we're seeing again that, the brain processing that's allocated to these body parts is a direct function of their sensitivity and acuity pattern recognition abilities. Now, what's missing from this touch research is sort of like the real world things that we do, right? So even though we can map out this information, which may be important for us, it fails to capture how people normally use the sense of touch, which is to hold an object in their hands. So I'm going to use some example here. I have my little elephant sculpture here, right? So not the best example here, but if I were to hold this in my hand, now it would be questionable if I were to take an object like this and blindfold a person and ask them to hold this in their hand and recognize what it is. But a lot of times with more everyday kinds of objects, you can do this sort of thing, right? People can recognize basic geometric shapes by touch easily enough. And they can recognize familiar everyday objects fairly well enough by holding them in their hands, right? But only when they are allowed to explore the object using active touch, right? That is, wrap your hands around it, move your hands around and explore the object, right? And so the question now is, what makes this different than passive touch? Well, in passive touch, the person is laying their hand flat and you just press a stimulus onto their hand, right? And in the situation like this, they're not likely to be very good at recognizing, even though they can report some things about how many points of contact they feel, they're not going to be able to say much about what it is that is touching them. But when they wrap their hand around it, then they can say what it is. So what we have done here is we're getting a little extra information here. We can perceive all these properties through active touch that we might not get through passive touch: shape, size, weight or mass, right? And texture as well, because when you run your hand across it, you can feel if something has a smooth texture versus a coarse texture. And even hardness, right? If you squeeze, you can detect, because this is made out of, I assume, calcite. And so it's pretty solid and hard and therefore resist any attempt to squeeze. But if it was a sponge, then clearly I could detect that change in the hardness. And so next question becomes, how do we get that information once we start letting our hands move around, right? And that means we're involving a little bit more than just the receptors in the skin, right? Because yes, even though the receptors in the skin are being stimulated when I touch this object, there's a little bit more going on here, because when I run my hands across my sculpture here, the sculpture's rigidity prevents my hands from moving, and it constrains the way I can move my hand around, right? And so that means that as I wrap my hand, if I just do this with an empty hand now, you can see that what's really going on is that I have to perceive the shape of my hand grip while I am exploring the object. And so there's something else that I'm extracting about this object, not just the way it contacts my skin, but also the way that my hand is constrained to explore and move around. And that means I have to perceive where my hand is, and the shapes and the orientation of all of my fingers. This is called proprioception. Proprio means self, and so self-perception in this case is referring to the perception of the position and posture of all of our body parts, right? The shape of my grasp as I hold on to something, but also, of course, just the orientation of my arms and my legs, my head and my neck, all of those body parts that have joints that can control their position. Those can all be felt via what we call proprioception. Now, as these body parts move around, like if I move my fingers across something and I can detect the texture, now feeling the movement of my body parts, that's called kinesthesis. And then, of course, we also, as we stand on a solid ground, we lean a little to the left and to the right. And as I walk on a nice, solid, stable surface, I can take even, steady steps. But if I'm on an uneven, imagine you're in a bouncy house like when you were a kid, right? And everything is uneven and you're kind of bouncy, then obviously in that case, your ability to detect the rigidity of the surface that you're standing on has a lot to do with that feeling the give, which you feel with your legs and your feet, obviously, but also because your posture is kind of, jumping all around and is very unstable. Now we're also going to involve the vestibular system, which is what we generally think of as your sense of balance. And these are organs based in your inner ear. But technically speaking, the vestibular system is really best considered to be an accelerometer. And so it detects a variety of different accelerations applied to the body. And of course, one important acceleration is the ever-present effect of gravity, right? Gravity is a specific linear acceleration of our bodies down to the earth at 9.81 meters per second squared. And so the presence of gravity activates the vestibular system. And if I am standing upright relative to gravity, that's going to create a particular response of the vestibular system. But if I'm starting to lean over one way or another, now I'm kind of leaning slightly perpendicular to the gravitational vector, and that's going to create a differential reaction out of the vestibular system. So talk a little bit more about that later at the end of the notes. But let's talk about proprioception first. So as noted, we need to use proprioception to perceive the orientation of our limbs. And one thing that we learned from studying proprioception is that people are actually really good at this, right? So when we think about human capabilities, here's something that people are good at. So what we have in this position matching task is a blindfolded person who has their left arm and their right arm kind of strapped to these rotating boards, right? And one is called the indicator and the other is the reference arm. So the reference arm is the arm that an experimenter will place at a specific angle, right? So they're going to move this up and down. They're going to move it up and down like this to get that arm at some angle. And now the subject's job is to take their left arm and indicate with their left arm the same angle, right? Essentially to try to match the orientation of their elbow. And the potentiometers in the base of this contraption can measure the exact angle that they've set it at to see how you can measure exactly to some angular degree how accurate a person can be at this task. And well, no matter where you set the reference arm at any number of different angles, people can do a pretty good job of matching it. And so you can see we can also do this with rotations around the knee as well. So matching orientations of the lower leg segments. So people are good at this, right? And then also this other thing I have on the left showing the two hands kind of coming down with a space between them like that. Here, I'm going to use my book here. So I got the book. And so if I were to put one finger on top of the book and then another finger, can't do this really well, right below the book, right? I'm bringing my fingers down, but there's a barrier between them. Question now, of course, is how good can I do this? The way this is typically done is that a person would sit at a table, kind of like we see with our subject in the position matching task, and they would place one finger on the underside of the table, and then they would be asked, now just reach with your other hand and bring it down on top and see if you can get your fingers lined up, on the opposite sides of the table. Sometimes we might rotate this vertically so that now you're sitting with one hand like this on a board, and then you just have to reach around with the other hand and get your two fingers lined up, right? Again, people are pretty good at this, and that more or less boils down to doing something as basic as closing your eyes and touching your nose with your finger. Again, this is something that people can generally do. But there are possibly some constraints and limits on what our abilities are when it comes to some proprioception stuff. So let's go to virtual reality, as we see on the bottom image here. So we see in this image a picture of a person wearing a head-mounted display looking at some virtual space, which includes, say, a three-dimensional rendering of some virtual hands there, right? And so whether they're doing, I don't know exactly what task they're doing there. They're making a gesture, which I think, a lot of VR applications involve gestural recognition. So a person makes a specific pinch with their finger, different fingers pinch on the thumb, and that indicates various, signals to the gestural recognition system that can activate various functions. But in this situation, we might also ask the question, when that person looks at their virtual hand and they can only see it, they can't feel the virtual hand. What they feel is their real hand, right? They're getting real proprioceptive feedback from where their hands really are in space. But then they're also looking at a virtual representation instead of looking at their real hands, right? So one thing we might ask is, how good is the VR system at accurately rendering the virtual hand in the right position so that it perfectly aligns with where the real hands are in space? And the reality is that the motion tracking might have a little bit of slop in it and lag in it that might cause the virtual hands to be rendered in a location other than where the real hands are. And now we might ask, well, so now what has to happen is the person has to integrate visual information about their hand location with proprioceptive information about their hand location. And how well do we do that? And how does this affect our reaching performance, right? So if I'm going to reach out and grab something, am I relying heavily on the visual information about where my hand is, or am I relying heavily on proprioceptive information about where my hand is? And if those two things are not in perfect alignment with each other, such as in a virtual environment like this, do we see some important errors now, right? We're going to start seeing errors in reaching performance because of this misalignment between the virtual and the real hand. One of the things that we've seen in this research is that you can draw a person's virtual hand 5 centimeters away from where the real hand is, and right at that boundary of that 5 centimeter boundary, that's an area that people tend to not notice, right? So anything from 0 to 5 centimeter offset of the virtual hand is not typically noticed as having been in the wrong position by the subject here. So once we start to deviate the virtual hand more than 5 centimeters away from where the real hand is, that's when people start to actually notice. Although the effect on reaching errors in VR has unfortunately not fully been studied. So there's some interesting room for future research here. It's, as I said, well known and confirmed and replicated that you have to move the virtual hand at least 5 centimeters away from the real hands in order for somebody to notice that. But whether they notice it or do not notice it, how does this affect reaching accuracy in VR? There's plenty of room for exploring that particular question, right? So let's try to put all of this together, right? Our touch, tactile, skin sense, along with proprioception, kinesthesis, and even the vestibular system. And what we want to say here is that what we're really doing with our sense of touch is that we use all of that to perceive our bodies. But of course, we're using our bodies to perceive objects that we come into contact with, things that we hold in our hand, the ground that we stand on, all of that stuff. We are feeling properties of the world because we come into that kind of physical contact with it. And that perceptual system is called haptics, right? Our ability to perceive the relationship between our bodies and the things that we come into physical contact with. So when we think about providing now in a virtual environment haptic information, right? So how do we do that in VR? Can we provide the kind of haptic feedback? So I was holding my elephant sculpture earlier. So when I hold this, it constrains how I can wrap my hands around it. And I can use that perception of my grip posture to feel something about the shape and solidity and size of this thing. So how do we replicate that in virtual reality? If we want to have people interacting in virtual environments and have a more realistic experience and maybe improve their performance, instead of just having visual and auditory information, can we give them some haptic information? So we see here the use of this haptic feedback device, which has the exoskeleton that constrains the way that your hand can grasp a virtual object. But in this situation, it's a little bit of a strange experience because the glove that the person's wearing is not providing any stimulation on the palm of the hand. That's just to hold the exoskeletal device in place. And so it's a weird kind of virtual haptics that just provides weird constraints on your grip without feeling anything in your grip. It's like an empty hand that still is holding on to something. And the question then becomes, in this kind of technology, what if we were to present people with objects of different shapes, and how accurate could they be at recognizing a sphere from an egg-shaped object, or a cube from a sphere even, right? How bad could it be? And again, unfortunately, we don't have a lot of information on this, right? So whether people can accurately judge through haptics the shape of an object or the size of an object with these devices is not quite clear, right? So are we good at virtual haptics? Nobody knows, right? Here's another case where we're going to use haptics now to perceive our self-motion. It's also famously referred to in the literature as visual kinesthesis, right? Visual information about your self-movement. So it's important to realize here that when it comes to perceiving your body, vision plays a role here, right? And so vision is part of kinesthesis. And certainly that plays a role when I see my hand moving, or if I'm reaching for something and I can see my hand moving, then I have both visual and kinesthetic information that is from the receptors in my arm, right? So there's, in addition to the touch receptors, I didn't mention this a minute ago, but in addition to the touch receptors in the skin, proprioception and kinesthesis is achieved because we have receptors embedded in the muscles and the tendons in the joints that provides this information about limb position. And so I have that body information about my arm moving, but I also have visual information about my arm moving. And so again, I've noted that we have to keep those two things calibrated with each other and integrated with each other. And in VR, all bets might be off, but in regular experiences, these should be naturally matched and calibrated with each other. But also think about another thing, which is when you're walking, you might not necessarily even be looking at your body, right? You're not looking down at your feet, so you're not necessarily going to see that you're walking, but you do experience something visually when you're walking, which is that you experience the visual consequences of walking, right? And so there's a particular visual motion that occurs as you walk around, and that provides information to your brain that you are walking, right? Just merely the visual experience that accompanies that. So in addition to the vestibular system that's going to feel walking, and your proprioceptive and kinesthetic information that feels your legs going left, right, you're going to have visual information that accompanies all of that. So all of these things now have to be integrated while you're walking, right? The proprioception and kinesthesis from your legs, vestibular information that tells you about your acceleration forward, and the visual consequences all need to match each other. And so here's where we have to worry about things like motion sickness, right? So when people get car sick, this is caused by the fact that there can be a discrepancy between the visual information that a person is getting about their linear acceleration forward versus the vestibular and haptic information that a person is getting about their linear and acceleration. And in those cases, those can be disconnected. And that's especially true when we think about, again, virtual reality, or flight simulators or driving simulators, or even movies like an IMAX movie where you have maybe a camera strapped to the bottom of a plane and it's flying over the ground. And so you're going to get this huge screen that gives you a very strong sense of self-motion there visually. In each of these cases, right, we can simulate self-motion in virtual reality and in movies and so forth. But a person is sitting still in a chair, so their body isn't actually subject to those same accelerations. And we get these conflicts that results in nausea. So what's going on here? So the first thing we want to do is to understand why vision plays such an important role in providing information about our self-movement. And our first example of that is one of the famous studies from the 70s called the moving room studies. And so what you can maybe gather from this image is that our researcher here, who is the one kneeling with their back to the camera, not the child, but the person on the outside who's holding onto this bar, And so they have constructed this little room that is really a false room that's hanging by ropes from inside a larger room. And what we're going to do, and the floors are the regular floor, right? But it's the three walls and the ceiling that are suspended, right? So we're going to bring a toddler in, and we're going to use a toddler because they don't yet have a complete, perfectly functioning sense of balance, right? They're still in that stage of mastering postural control. But we're going to have the parents there to catch them if they fall, right? And so as that child faces the far wall, what our researcher is going to do is grab this bar and they're going to pull back a little bit, and it's going to cause all of the three walls in the ceiling to move towards that child's face, right? Now, what would normally happen that in real life that would cause the wall in front of you to get closer? Walls don't normally move, right? But typically it would be because you are falling, as if your postural maintenance was starting to fail and you were going to tilt forward a little bit. That would cause a visual consequence to occur, which would be this visual expansion of the wall in front of you as it gets closer. So if visual expansion on the wall in front of you normally accompanies falling forward, then your brain's going to say, well, the appropriate thing for me to do in this case is to try to lean backwards, because if I'm falling forward, I want to counteract that by leaning backwards so that I don't fall on my face. So that's what the child in this situation does, is the child tries to lean backwards when that wall starts to move. But since the child is actually not falling forward, this attempt to lean backwards actually causes them to fall down on their bottom. And if we do the other thing, if we move the wall away from them, that would normally occur when you are falling backwards. So the child's attempt to account for that is to lean forward, and they end up stumbling forward a little bit when the wall moves away from them. And so this is now revealing here that even when it comes to just simple postural control, standing upright without tipping over is something that certainly, again, the proprioception and kinesthesis from your legs, as well as the vestibular system, play a role. But this highlights that even vision is such a powerful influence on this that it can override those other systems, right? So the child's vestibular system is telling them that they are not falling, but the visual system tells them that they are falling. And what happens is that they end up stumbling because the brain is essentially listening more to the visual input than it is to the vestibular input at this point. So clearly, vision plays a very important role here in regulating posture. And these are the moving room studies. But something else that's very important here. So why do we have this really strong interconnection between the visual and the vestibular system? It's called the vestibulo-ocular reflex, VOR, right? Now, think about this, right? When you move your head around, let's try this for yourself. Pick any stationary object in your room and just keep your eyes locked on it. And then try to just turn your head as you keep your eyes fixed on that. And what you'll find is that you don't have any difficulty doing this, right? That no matter how you move your head and what direction and so forth, your eyes can stay locked pretty well on whatever object you're fixated on. So what is it that keeps your eyes locked in position as your head moves around? Well, what that means is that in order to, every time your head moves, say this way, but I want to have my eyes looking this way, I have to make sure that my eyes perfectly counter rotate in the way that's exactly the opposite of every head movement, right? So to keep your eyes fixated on an object while your head moves, the eyes always counter rotate in a way that's exactly proportional, but in the opposite direction of a head rotation. And the way this works is through the vestibular system. Here's just another picture of the moving room effect, right? And so the vestibular system has to detect the head rotations, and then that has to then send some information to a part of the brain that regulates the eye muscles so that the eye muscles can counter rotate the eyes in a way that quickly and accurately counteracts the effect of any head rotation. So how does the vestibular system work? Let's do the real quick version of it here. We have inside the inner ear 5 organs here, plus the cochlea. The cochlea is for hearing, so don't worry about that part of it, but they're interconnected. So it's going to be shown in the picture here. But we have 3 semicircular canals and 2 fluid-filled sacs called the utricle and the saccule. So the utricle and the saccule are part of a linear accelerometer system, right? So what's happening here is that these are just fluid-filled sacs that are lined with hair cells, and floating around inside of the utricle and saccule are small bony particles called otoliths, which just means ear stones. And when you're standing upright relative to gravity, then all of the otoliths will sink down to the bottom of the utricle and saccule, and that tells your brain, I'm standing upright relative to gravity. If you were laying on your side or hanging upside down, then the otoliths would sink to different regions of the sides or tops of the utricle and saccule, right? So that's linear acceleration, mostly just gravitational acceleration at this point. But those head movements that I'm talking about, in order to keep your gaze stabilized and fixated on an object while your head turns, now we have to detect rotational accelerations. And this is where the three semicircular canals come in. So these three semicircular canals are oriented approximately perpendicular to each other. So we have one that's oriented kind of in this flat horizontal plane, and then another one that's oriented kind of here in this vertical plane, and then another one that's oriented perpendicular to that in this vertical plane. So now what we have is the ability to detect rotations in this horizontal plane, like this, and I'm doing this with my head and my hand, right? And this would be essentially, if we use our rotational acceleration terms, this is the yaw, right? And then we can also do this, which is pitch, right? And then this kind of rotation is considered roll. So we can detect the pitch, roll, and yaw of the head by having three semicircular canals oriented in different planes, right? Now, how do they work? I've already got the pictures here, right? So this is a picture that shows how the utricle and saccule work, right? We're seeing here that in the interior lining on the bottom of the this image here, the little hair cells that stick up and the otoliths cause these things to sink down and put pressure on the bottom of the utricle and saccule, landing on those hair cells that tell the person, that tells the brain that this person is standing upright. Also, in this case, if we're looking at a sprinter here, what's going to happen is that as the sprinter sprints forward, you're going to have a linear acceleration applied to the head, in which case, just like what happens, imagine when you're in a car and you're sitting still and then you step on the gas and floor it, right? And you kind of go back in your seat a little bit. Same thing would happen to our the otoliths and the hair cells here, is that they're going to all kind of fall backwards, and that's, again, some information about a linear acceleration. But inside the semicircular canal, so this is the top half of the image, at the base of each canal is a little bulging area that has this little paintbrush type shaped tuft of hair cells sticking up, and it's called the cupula. And the cupula, again, because it's a bunch of hair cells, when we have these head rotations, the fluid inside the canal is just basically sloshing around in one of those orientations. And that's going to cause the cupula to kind of bend one way versus bend another, to provide information about which canal is being stimulated. And that's going to tell us the axis of rotation. And then also what's the direction of the bend of the cupula. And that tells us now the direction along that axis of rotation. This is also, again, more pictures showing the same thing, right? Showing how the angular or rotational acceleration of the head causes the displacement of the cupula in a specific direction and in a specific plane. So now to get back to our vestibular ocular reflex, or VOR, here we actually have kind of a wiring diagram that shows how the detection of angular acceleration in the vestibular system sends a signal to the midbrain that then causes simultaneous excitation and inhibition of certain ocular muscles that are going to trigger the exact opposite rotation of the eyes. And so we're going to get this counter rotation, right? So it's important for these two systems to be in good synchrony with each other. And what happens when you're in a simulator, like a flight simulator or virtual reality or an IMAX movie, or in a car even, or even on a boat, another good example is seasickness, right? Is that this can cause a conflict between the visual and the vestibular system about what kind of acceleration is being detected here. And what we see is that there can be some individual differences, right? Some people just don't experience it. Some people do. And so one thing we want to try to understand is, can we predict someone's susceptibility to motion sickness and therefore maybe not give them exposure to these kinds of displays, right? So you want to maybe be able to rule out the tendency to get sick beforehand. There's actually a questionnaire. It's called the Motion Sickness History Questionnaire that is used to detect a person's likelihood of experiencing simulator sickness. So you would administer this before you put them into a simulator or virtual environment. There's also simulator sickness symptomology questionnaires so that you can ask people every 15 to 20 minutes to report their symptoms and pull them out before they get worse, right? And so one thing is that we also might think that one of the reasons why some people are more sensitive to simulator sickness is because of individual differences in the gain of the VOR system. So the gain here applies to the idea that once we detect a certain magnitude of rotation with the vestibular system, then we have to perform the appropriate counter rotations. But if the gain in that system is too high, that means the counter rotations are too strong, all right, and the eyes over-rotate. You can also have too low of a gain in which the counter rotations of the eyes are insufficient. And so in those situations where the gain in the system or the phase is more like a lag in the system, could cause the counter rotations to be insufficient, and that might then mean that that person's VOR reflex, the reflex is really not as stable as another person's, and that might mean then that they're more susceptible because of that. All right, well, I think we've covered enough touch and haptics, and we are now ready to move on away from all of the human sensory stuff.